Hello and welcome. This is Marcel Bimmer from Monash University in Australia. Welcome to session P25 on fuzzing. I'm really excited about the talks. There are 5 technical papers in this session. Each talk will be 8 minutes long, and there's going to be a 3 minutes Q&A. Because of a 1 minute lag between Zoom and Clouder, not all questions might be answered, so please go to the Baekje room on Slack if you to meet the presenters after the talk. So the first session is going to be Hai-Chun talking about type state guided fuzzing for discovering use of the free vulnerabilities.
Hello everyone, can you see my screen?
Yes.
Okay, I'll begin. Hello everyone, my name is Hai-Chun Wang. I'm from Andean Nation. My paper is a type state guided fuzzer for discovery use of the free vulnerability. Fuzzy technique is an automated software testing technique which provides invalid, unexpected, or random data to a program. Fuzzy technique is mainly divided into 2 types. One is generation-based fuzzy, which generates inputs from templates, such as grammar specification. The other type is mutation-based fuzzy. It randomly mutates inputs from seed test case. This is also the most popular fuzzy technique. Although fuzzy technique is very popular, there are still some challenges we should overcome. This figure is the general workflow of fuzzy technique. In this figure, an important component is coverage information, because it determines which seed would be put into seed pool for further mutation. A big challenge is whether the existing branch coverage is enough for detect all vulnerability. For example, use after free vulnerability. I'll use an example to illustrate. In this program, at 940, it uses the free memory. Therefore, this is a typical use after free vulnerability. However, for this program, we use the branch coverage guided fuzzer, such as FL. We did not find this UAF vulnerability within 24 hours. In this figure, we can see that 4 test case can cover all branches. Therefore, the late test case would be discarded. As a result, FL has little chance to detect this UAF. To expose this UAF vulnerability, a test case should cover 9, 4, 7, 10, 40 together. To generate this kind of test case, 2 challenges should address. One is how to identify the above operation sequence. The second is how to generate a test case to cover this operation sequence. Intuitively, to detect this UAF, we should generate a test case first cover 9, 7, then 9, 10, and then 940. This is the ideal way to detect this UAF vulnerability. Of course, this is also our target of our approach. Based on this ideal way, we develop our UAF fuzzer. In this section, I'll introduce our type state guided fuzzer for discovery UAF vulnerability. Our approach is divided into 3 components. The first is the static type state analysis. The second is the instrumentation. The third part is the fuzzy loop. I'll introduce them in detail in the next 3 slides. In the static type state analysis, one input is type state property, which describes the property of the vulnerability. For example, The left figure is the type state property of UAF vulnerability. Based on the type state and type state property, we use the static analysis to identify the operation sequence which violate the type state property. For example, the line 4, 7, 10, 40 violate the type stable property of UAF vulnerability. Based on the operation sequence, we instrument the program. Our instrumentation is divided into 2 steps. In the first step, we instrument each statement SI to determine whether SI is executed. In the second step, we retrieve the execution information of SG, which is before SI in the operation sequence. Besides, we also introduce the information flow entropy to build the relationship input bias and the program statement. Therefore, we know where to mutate the input bias to reach some program statements. As a result, we greatly improve the efficiency of our mutation. The second part is our fuzzy loop. We introduce 3 optimization. The first is seed selection. We select the seed which cover more operation sequence. The second is mutation strategy. We prefer to mutate input fields that relates to more operation sequence. The third optimization is feedback. We don't use the branch coverage guidance. We use the operation sequence to guide our fuzzy loop. The above 3 optimization greatly improve the effectiveness of our approach for discovery UAF vulnerability. In the last section, we evaluate our UAF. Since we introduced the static analysis, we evaluate its overhead. In the column OS, we list the number of identified the operation sequence. In the last column, we show the time overhead by static analysis. On average, the time overhead is less than half an hour. Therefore, the overhead by static analysis is acceptable. This table shows the time to expose the UAF vulnerability. In this table, we can see that our approach performs best in almost programs. This column shows that our approach finds all vulnerability within 24 hours. However, the other fuzzers may miss some vulnerabilities. The last 2 rows shows the speeds up our approach achieved compared to other fuzzers. Since the fuzzy technique has some randomness, we also perform statistical tests. In this table, we can see that our approach significantly outperforms other fuzzers in almost programs. In the last 3 slides, we show the operation sequence coverage over time. In these 3 slides, we can see that our approach also significantly outperforms other fuzzers in the operation sequence coverage. This is also the reason why our approach finds the UAF vulnerability faster than other fuzzers. That's all. Thank you.
Wonderful, right on time. So there's one question from Caroline, and she asks, how do you determine which fields are related to operation sequences for mutation targeting?
Here we introduce the information flow. We introduce the information flow entropy because for example, we mutate some input bias. Then we can instrument the program. We can get the which branch is affected. Based on this relationship, we can determine which input fields may affect which program statement. Then if we want to switch the branch, we can mutate this input fields.
Okay, I also have some questions, and the audience is welcome to add their questions to Slido on Clouder. So my question is, so you generate more seeds. You earlier said that you you even remove coverage guidance. You add more seeds that exercise longer operation sequences, and prioritize operation sequences, seeds that exercise more operation sequences. So I'm just wondering how this influences the discovery of other kinds of bugs that are not use after free bugs. Do you investigate that as well?
Can you repeat the last statements? I didn't hear it clearly.
Yes, so you focus particularly on use after free vulnerabilities.
Yes.
What about other kinds of vulnerabilities? Is there the effectiveness in terms of discovering, say, buffer overflow vulnerabilities reduced, or is it the same? And if it is reduced, how do we tackle that?
First, we focus on the complicated vulnerabilities because for example, the buffer overflow vulnerabilities can be easily detected by almost fuzzy technique because buffer overflow has no long context. Therefore, the most general fuzzy technique can find buffer overflow. Our UAF focus on the complicated vulnerability. For example, some vulnerability should be discovered in context, and our fuzzer is a framework. If we can model the context of the vulnerability, for example, we can use our type state to model the other kind of vulnerability. For example, the misuse of the API. We can model this kind of vulnerability into a type state. If we can model this vulnerability, we can use our operation sequence guided fuzzer to find this kind of vulnerability.
Yeah, thanks, Haijun. So I think you can easily also argue that you could integrate several fuzzers and run them like AFL together with your technique and run them simultaneously in the same program to find different kinds of bugs with different fuzzers. So thanks again, Haijun. The next speaker is going to be Tai from the Singapore Management University, and he's going to talk about SFuzz, an efficient adaptive fuzzer for Solidity smart contracts.
Okay, can you see my screen?
Yes.
Okay, so I'm Tai from Singapore Management University. Today I present my paper, SFuzz, an efficient adaptive fuzzer for 3D smart contract. As we all know that smart contract is a program executed on top of Ethereum blockchain. So because smart contract often hold valuable digital assets, it's become a good target for hacker. The table here shows 4 well-known hacks in the past, where DAOs is the most infamous one. Hackers stole about 3.6 million Ether, which is equivalent to 80 million US dollars at that time. Smart contract manage money, but they cannot amend this once they are deployed. To solve that problem, we must test smart contract thoroughly before we deploy them to Ethereum blockchain. So fuzzing is one popular method to uncover bugs. And AFL is the most popular fuzzer for C and C++ programs. It's your evolutionary algorithm. The idea of fuzzing is simple. We randomly fit different permutations of an input into a program until one of those permutations reveal a vulnerability. So as you can see the mutation process on the right of the slide, the red cross indicates a test case they are not selected to mutate. So fuzzer is easy to implement. However, it is inefficient due to random mutation and inefficient objective function. The criteria to keep or discard an input for the next mutation is the objective function of fuzzer and AFL select inputs, which have covered new branches. We have AFL for C and C++ programs. Why don't we have another variation for smart contracts? Because smart contracts are different from C and C++ programs, we have to deal with some challenges. For example, like code instrument, we have to input code in the smart contract to get branch coverage. We have to set up environment. For example, we simulate the whole blockchain to execute transaction with our miner. We have to initialize account with some balances, set up global variable, for example, block number or block timestamp. We have to provide an input format and write a decoder and encoder to make sure that EVM can understand and execute that input. The finger on the left is the sample inputs for the smart contract on the right. This smart contract has two functions, try and start with game. We allocate 2 slots on the bottom for the parameter of function start with game and 1 slot for the parameter of function try. We also support dynamic size inputs by declaring the size of dynamic variable at the beginning of the input. We also support different sequences of function call by changing the order of function in the sample input. Here we introduce our tool as first. It is the combination of AFL smart contract and SBSD. SBSD stands for search-based software testing, which refer to the methods that we can use to construct the multi-objective function. However, our multi-objective functions is lightweight because we only keep one input for one uncovered branch. In practical, we have to deal with 10 to 15 uncovered branches one time. Here we show the differences between objective functions of AFL and S1. Both AFL and S1 aim to cover all branches of the program on the left. Both test case is equal to 0 and it's equal to 10 cover 3 out of 4 branches. One remaining branch is equal to 100. AFL discard 99, even though it's really close to 100. But at first it's different, it skipped 99 and finally reached 100 and cover all branches in the program. However, why do we know 99 is equal to mutate, not 90? So here is the answer. We calculate distance between a test case and uncovered branch. It's equal to 100. Formula is given in the slide. A smaller distance is better. In our example, distance of 99 is 2 and distance of 90 is 11. That's why we choose 99, not 90. For the evaluation, we conduct many experiments to evaluate the effectiveness of efforts. We run efforts against 4,112 smart contracts collected from website Etherscan. A smart contract is run for 2 minutes. Then we compare with Argente, a famous symbolic execution tool, and contract fuzzer, which is similar to our work. From the experiment results, we answer 4 research questions. First questions, how many test cases are generated and executed per second by efforts? The finger shows the speed of efforts in comparison with Argente and contract fuzzer. Each bar represents around 410 contracts and they are sorted by speed. On average, efforts generates and execute about 200 test cases per second. Argente is 16 test cases per second and contract fuzzer is 6 test cases per minute. On average, efforts is 30 times faster than Argente and contract fuzzer. So the second question is how many branches are covered by efforts? On the left, we compare efforts and contract fuzzer. Blue bar indicate that efforts outperform contract fuzzer. On the right, effort cannot be better than Argente. The reason is that Argente analyze every function separately. Therefore, the global variable can take arbitrary value without considering their initial values. Is it not correct in the real smart contract? The third question is how many vulnerabilities discovered by experts? We focus on 9 types of vulnerability. They are shown in the table. The results show that experts found more bugs than contract fuzzer and Argente, except reentrancy and integer overflow, underflow. However, in the cases, Argente have low true positive. The last question is how many branches are covered by our lightweight objective function? In the figure, we count percentage of test cases generated by AFL and our strategies. On average, experts contribute about 30% of generated test cases. So the key takeaway of our paper are we combine AFL and smart contract and lightweight SPST to create efforts. It's significantly more reliable, faster, and more effective than existing fuzzer. So the open source of efforts is available in GitHub, and we also have an online version at GasTry website. So they are listed in the slide. I think this is the end of my presentation. Thanks for listening.
Thanks, Tai. So there are no questions from the audience. Of course, the audience is again invited to post questions on Slido, but I have a question. So you show an extension of gray box fuzzing with SPST, and particularly with concepts like branch distance and multi-objective search, and you apply that to Ethereum smart contracts. So I'm wondering what makes smart contracts particularly challenging for gray box fuzzing, and why, or is your approach more general than smart contracts?
I think smart contracts challenging because of some reason here. Sorry, I moved to that slide. For the smart contract, we have to set up the blockchain to execute the contract. This is difficult than the normal program. We have to, because many contracts can interact with each other, we have to initialize some accounts and set up an environment. Like we have to set up many things to execute the smart contract. This is different from the normal program like C and C++ program, I think.
Okay, and my next question is, so you apply multi-objective search, and in your case, each branch that you haven't been able to negate is becoming one objective, if I understand correctly. So there are other approaches in search-based software testing for increasing coverage, and particularly you can cast this as a single objective function and say increase coverage. So your fitness function is just coverage. So I'm wondering whether you compared your idea of multi-objective search versus simple single objective search.
Excuse me, I'm not sure that I can understand.
What motivated you to use multi-objective search for this?
So multiple objective search. This is because we cannot build the whole control flow graph of the smart contract, because it's not trivial to build from the scratch, and then we just build on the fly. And for each uncovered branch, we have to build multiple objective functions to try to cover each uncovered branch. So I think that's the difference. That's why we choose a multi-objective function.
So there's a question from the audience. It turns out Oriente is still better in code coverage than SFuzz from the evaluation. Did you analyze what's the difference between them? Maybe a short answer.
So I'm not sure.
Should I repeat the question?
Yes, can you just repeat the question?
Yeah, so it turns out that Oriente is still better in code coverage than SFuzz in terms of evaluation. Did you analyze what's the difference between them?
I think I haven't analyzed it, the difference between oriented.
Okay. So unfortunately, we can't check with the question, with the person who was asking the question, what in which respect he's interested in the difference. But yeah, thanks again for your talk, Tai. The next talk is going to be Iftikhar from University of California in Irvine. And the talk is going to be about planning for untangling, predicting the difficulty of merge conflicts.
Thank you, Marcel. Can you hear me?
Yes.
And can you see the screen? Can you see the slides?
Yes.
Yep. Thank you. Thank you and welcome everyone. Welcome to today's talk, Planning for Untangling, Predicting the Difficulty of Merge Conflicts. I'm Iftekhar. So this talk or this work is a collaboration between Oregon State University and University of California, Irvine. So collaboration drives modern software development. All large software projects are developed by a team. In 2017, over 4,000 individuals contributed patches to Linux kernel. And another example is Windows Vista, which was developed by 3,000 developers in 21 teams spread over 3 continents. And a more recent example is TensorFlow in 2019, which had 9,900 individuals contributing to it. Now, this collaborative software development has many benefits. We all know that, but it has some negative side effects as well, or side effects, you may say. So merge conflict is one of such side effects. So what is merge conflict? Merge conflict is something that happens when multiple people try to work on same piece of code. For example, if you look at the slide, top of the slide, there was master branch, and then there was Alice and Bob who were trying to work on their own branches. They created copies of the master branch. And at some point, both of them modified file F2. So when they tried to merge the code back into the master branch, they ran into conflict on file F2. And on the bottom of the screen, you can see 2 different ways how merge conflicts are visualized. On the left, this is how it's shown on GitHub interface. And on the right, this is how it's shown on command line interface. So at this point, you might be wondering, okay, why should we care about merge conflict? We should care about it because merge conflicts are challenges or to collaborative development. So when it happens, a developer actually has to interrupt their work, focus on solving it, and then only they can move on to the next task. So it becomes an immediate concern for the developer. And also this happens very frequently. Research shows that 1 out of 5 merges result in a conflict. And on top, it has impact on quality, both in terms of long-term maintenance issues and also in terms of faults. So due to all these impacts these merge conflicts have, researchers have been looking at various aspects of it. On the right side, you can see researchers have come up with different stages of processing or handling a merge conflict, which has 5 stages. Prior research also tried to look into coming up with ways of prevention, early detection, and of course, helping developers by providing assistance. And another thread of work looked into understanding the resolution difficulty, primarily by looking into doing interviews and surveys. Now, in this work, what we try to do is we focused on predicting the difficulty of a potential merge conflict in order to help developers prioritize the merge conflicts to inspect, accomplish more things given a tight schedule, and not waste their reviewing effort on trivial merge conflict resolution. And of course, identifying features that has impact on the difficulty of a merge conflict. To be more concrete, we were focusing on stage 3 or step 3, the planning phase, how to help in that phase. So the research question that we set out to answer were, can we predict the difficulty of merge conflicts? Which characteristics are associated with this difficulty? And can we do cross-project training to predict merge conflicts to solve the cold start problem? So due to lack of time, I will not go through the details of the steps that we did in this study. I will give a very quick overview. So we started with selecting a large number of projects from GitHub and then apply different kinds of selection criteria, such as like should not be a fork project. The project should compile. Then a certain number of developers have to be there. Duration of the project, the things that are usually used in literature. So after that, we identified 128 projects. Then we did the conflict identification, where we started by extracting around 556,000 commits. From there, we identified 36,000 merge commits and then 6,380 conflict commits. Then for these conflict commits, merge conflict commits, we collected process and product metrics in 5 different categories, 16 of them. And these metrics were selected based on existing literature. So after that, we applied the machine learning pipeline where we did usual feature selection, model training, evaluation, comparison, and we ended up with our final model. And to answer the third question, we did cross-project prediction where we trained the model on project A and then applied it on project B. So what we saw was that, yes, to answer the RQ first question, using Baekje classifier, we can actually predict the difficulty of a merge conflict with quite good performance. So AUC value of 0.85, and we compared with 4 other different classifiers. So once we saw that, yes, we can predict the difficulty of a conflict, the next question became, what are the factors that makes it difficult? So we applied feature subset selection technique on the model that we built, those 16 metrics, and from which 12 were used in the model that was built. So what we saw is complexity, diffusion, size, development pattern are significant factors for predicting difficulty of merge conflicts. So then we also wanted to investigate, is it the same factors that are identified to be significant by both humans and by feature subset selection technique? So for that, we built on the top of the work of McKee et al., where they had interviewed developers for identifying the factors that developers think are important for resolving merge conflict. So as you can see in the table, one of the factors, the top one, complexity, is identified as to be important by both FSS and humans. But interestingly, there are certain factors that were not identified to be important by the humans, not as important by the humans, but were important according to the FSS criteria, so such as dependency. Now, this could happen, this discrepancy could happen due to many reasons, maybe lack of expertise or lack of experience, maybe one of those. However, we did not investigate for the reason, so which needs further investigation and would be interesting future work. And to answer the third research question, can we actually do cross-project training? Yes, we can do cross-project prediction and with quite good performance. So as you can see here, we can do with AUC value of 0.85, as high as 0.85 and 0.6 on average. So what does all these mean in terms of implications and future work? So what it means is code with high complexity obviously makes it difficult to handle and manage. And then diffusion matters. So longer a branch goes on and the larger number of people are contributing them, it becomes more difficult to manage those tangled changes. And then more central a piece of code is, the more difficult it becomes to resolve the conflicts. And obviously bigger is more problematic. And in terms of future work, we have just scratched the surface. What we have done is we have shown that with high accuracy, you can predict the difficulty of a merge conflict even before it happens. However, it's not perfect, right? So there is still room for improvement for both within and across projects. And the other interesting area is this metrics that we identified to be useful or important. These metrics, we did not look into any kind of threshold of them. So there may be a point after which these metrics actually pushes a merge conflict from being trivial to severe. We didn't investigate that. So identifying or investigating those thresholds and then using those thresholds for prioritizing the merge conflicts would be a very interesting research direction. Thank you, and I would like to answer any questions if you have.
So there's no question from the audience, so I'll just ask a short question. What is your ground truth for establishing the difficulty of a merge conflict?
So the ground truth was like 2 independent researchers manually looked at the conflicts, and then based on how difficult it is, based on how much effort it would take to resolve those conflicts, we label those as trivial or severe merge conflicts.
And a question from the audience is, how would you use the predictions to improve the project management?
Right, so that's actually a very interesting question. So all these metrics that we identified to be significantly impactful, all of these you can calculate beforehand, right? Even before the merge conflict happens. And the existing merge conflict, not prediction, but merge conflict indication tools that exist there, right? Like for showing that, okay, there is a merge conflict is problematic. So these could be added on those tools without adding a lot of overhead. So then it could be also made part of continuous integration or even IDE. So that way it can help in managing the project, because if you can somehow see that, okay, this merge conflict, which there is a merge conflict which is about to happen and which is going to be severe, of course you can allocate resource accordingly.
Okay, thanks, Iftikhar, again, for the great talk.
Thank you.
The next speaker is going to be Akont from Tennessee Technical University, and he's going to talk about Gang of 8, a defect taxonomy for infrastructure as code scripts.
Thanks, Marcel. Can you hear me?
Yes.
Can you see my screen?
Yes.
All right. Hello, everyone. A warm welcome to our presentation titled Gang of 8, a defect taxonomy for infrastructure as code scripts. I am Akont from Tennessee Technological University. This paper was co-authored with Ifat Farhana, Chris Pernin, and Laurie Williams from NC State University. The industry, the information technology industry in recent years have gone a major transformation with respect to how they manage configurations. So now they're using automation and also treating configuration management as first-class artifacts or first-class citizens. And by that, I mean, just like regular source code, they're applying version control and quality control on these configuration management artifacts. Examples of tools include Ansible, Chef, and Puppet, and some of you might have already be using it or are interested in using it to automate your cloud infrastructure. So this practice is not an isolated event. It has been going along since early 2000s, say around 2005, and there are a wide range of IT organizations who are using it. So on one hand, we see typical software organizations who deliver software and services like Mozilla are using it, and that helped them to reduce their manual efforts by 99%, which is very impressive. And then there are companies who are not technically tech companies, but they still have a big computing infrastructure like Ambit Energy, Intercontinental Exchange, and NASA. And all of these companies have reported to have benefits from the use of infrastructure as code. So this practice, this particular anecdotal evidence shows that not only IAC is being used, it is delivering benefits for these IT organizations. However, there's a problem, and the problem is related to quality issues. So let's say we have this hypothetical practitioner who's developing the script. Inadvertently, this particular bug gets introduced in the script, it's executed, and then this bug propagates to all the provisioned instances, and that creates a lot of problems. This hypothetical scenario is it's not entirely imaginative in the sense that we do see anecdotal evidence related to this. So for example, AWS uses infrastructure as code, and a bug caused this service disruption in the whole Northern Virginia region. And then there is the example of GitHub, which experienced DNS outages related to bugs in infrastructure as code. So, and it shows that the studying bugs for infrastructure as code scripts, or IAC in short, is important because a lot of teams and companies rely on these companies like AWS and GitHub to deliver their software and services to end users. So whenever there is a disruption on their side, on the side of AWS and GitHub, then that creates problems for the users of AWS and GitHub. So all of these anecdotal evidence motivated us to study this problem systematically. And when we started looking at this problem, we also looked around to see if studying bugs or defects for IAC scripts could be of relevance to practitioners. And we noticed that it is the case. So for example, this particular Reddit snippet shows that a certain practitioner wants to adopt Puppet, which is a popular tool to implement IAC. But the practitioner wants some more pointers or insights on the defects that happen for IAC scripts. So both anecdotal evidence and also the need for scientific investigation motivated our research. In short, We tried to achieve the following objective, which is we wanted to guide our practice. We wanted to help practitioners improve the quality of ISC scripts by constructing a defect taxonomy. So it's going to be a category of defects for ISC scripts. So we tackled these following research questions. The first one was related to categories. The second one was related to practitioner perception, which was more trying to understand to what extent our findings make sense to practitioners. And then frequency, where we try to quantify how frequent or prevalent the identified defect categories are. So what we did was we started with mining repositories from a company called OpenStack, who have made their Puppet scripts available. We mined some defect-related commits. These commits also have tags or identifiers to bug reports. So we collected information from commits as well as from bug reports. We constructed commit messages to systematically understand them. And the way we did was that two independent raters, the first author and the second author, we both looked at them independently, and we came up with a set of categories. We resolved our disagreements, and in the end, we came up with the categories that needed to answer RQ1. For RQ2, what we did was we again mined repositories, collected emails from practitioners who are involved in modifying Puppet scripts. Then we sent out surveys, and from the surveys, we designed the survey in a way that they give an overview of how likely they're likely to agree that a certain category is actually a defect category. And we also made options to provide additional feedback on the survey. For frequency analysis, we wanted to do something that could be done at scale. So from the defect-related commits, we extracted patterns. We applied natural language processing techniques like dependency parsing. And from there, we generated rules, and the tool called Automatic Categorizer for Infrastructure as Code defects is basically a realization of these rules that could be used to identify defects at scale. So now, after we built the tool, the next step was to collect the repositories. So we looked into 3 organizations: Mozilla, OpenStack, Wikimedia, and we also looked into repositories from GitHub. So we systematically filtered them. We ran the tool against all the commits where Puppet scripts are modified, and then we quantified the identified defect frequency. So what did we find? So altogether, we identified 8 defect categories. Some of the defect categories are prevalent in other types of software like blockchain, machine learning, deep learning. But there was one category which is very unique to infrastructure as code, which I would focus a little bit more. So there were, like I said, there were conditional defects, configuration data defects. So these are these defects reflect configuration data for storage, file system, network, user credentials, and so on. The category that was unique to infrastructure as code was idempotency, which is basically the result of executing a script should be the same as the first execution when you execute the script multiple times. So the provision infrastructure that you just set up should remain in the same state as it was in the first execution. So unlike previously reported literature that studies defect categories, we noticed that this is very unique to infrastructure as code. And this could be of interest to conduct more research in this area. The practitioner results were interesting. So we noticed that there are varying perceptions on what the practitioners agree with and what are their opinions about it. So we noticed that idempotency is the most agreed upon defect category, whereas the subcategory service was the least agreed upon defect category. So we also noticed the most frequent defect category configuration data to be up there, but it's not the most frequent one. From the collected survey responses, we noticed some interesting comments on perceptions as well. So on one hand, we see practitioners to say idempotency and conditional are the 2 key ones. On the other hand, we say that we see another practitioner to say that debugging dependency loops is tricky and happens often. So these varying perceptions tells us that with respect to defect category prioritization, it could be interesting to see. And they mentioned other categories as well. We noticed configuration data to be frequent, and we did temporal analysis, and we saw that it remains dominant from 2005 to 2019. The implications of our work is that it can be helpful for benchmarks, it can be helpful for DevOps-related classes, and it can also be helpful for configuration-related repairs. So in short, we systematically analyzed defect categories. We constructed a tool to make the analysis scalable. And we also discussed the implications of our work related to benchmark for researchers, practitioners, and in the education domain. So with that, I would like to conclude my presentation, and I'm happy to take questions. Thank you.
Thanks so much, Akund. There's a question from the audience. The question is, do you see any difference in frequency of categories compared to other types of coding bugs?
By other type of coding bugs, I'm thinking other types of languages, or
yeah.
Yeah, go ahead. So my hypothesis is that it could, because configuration scripts are, or IOC scripts are used a lot to automate these in computing infrastructure, and that typically involves a lot of operations related to configuration. This frequency could be, the dominance of configuration data frequency could be very unique to IOC as well. But to answer that more conclusively, we need to do another study where we study the frequencies across all types of software.
Maybe another short question for myself. So you talk about opportunities to automatically repair some of the defects. So I'm wondering how complex these defects are, for instance, configuration defects.
Based on my understanding, some of them might be easy to fix. So maybe someone is using, while provisioning a firewall, someone is using a wrong port. So instead of the typical 80 port or 8080 port for HTTP, someone is using something like 79 or 77. But it is also dependent on the context. So from when we did our security analysis study from at ICSI 2019, we noticed that there are certain contexts that matters to derive what action should be needed to take action to repair a security problem. So my feeling is that the same could be applied here as well. So just the ability to generate automated program repair, automated repairs, configuration repairs might not be applicable for our practitioners because they all have their unique context.
Thanks, Akund. Our next speaker is going to be Tegan from University of California, Santa Barbara, and she's going to talk about JVM fuzzing for JIT-induced side channel detection.
Hi, everyone. I'm Tegan Brennan, a PhD candidate from the University of California, Santa Barbara. Today, I'll be presenting my work with Shimanta Saha and Tevfik Bolton on JVM fuzzing for JIT-induced side channel detection. In general, side channel vulnerabilities in software arise due to observable differences across program paths. As an example, consider the equals function here. This function compares a guess and a stored password character by character. As soon as a mismatch is detected, this function returns early, introducing a side channel in time that allows some observer to determine how many characters of the guess match that of the stored password. We can experimentally check this side channel. To the right, I show the results of two different experiments. The violin plot in blue shows the execution time distribution of this function when the first character of the guess does not match that of the password. The violin plot in green shows the execution time behavior of the function when the first characters do match. These two execution time distributions are distinguishable, illustrating the side channel we hypothesized about earlier. This side channel was due to the early return in the previous function. So to fix it, one might think, well, how about we remove that early return and instead ensure that the same amount of work is done regardless of whether the characters match. As a result, a developer might code the equals safe function shown here. But is this function really safe? Once again, we can go ahead and experiment. To the right, I show the results of the same experiments run on this new equals safe function. Now, these two execution time distributions look pretty indistinguishable. So has the side channel really been eliminated? Well, one crucial bit of information that I've kept from you is that I ran this experiment with just-in-time compilation disabled. When I enable JIT and run the same experiment, the story has completely changed and a side channel has arisen. This side channel is due to just-in-time compilation. As just-in-time compilation attempts to optimize paths that it deems hot, it can actually introduce timing side channels even into code that appears balanced at the source code level. The reason for these side channels is an imbalance in the input distribution of the program that leads the runtime to favor certain program behaviors. Just-in-time compilation is crucial to the performance of many modern programming languages, such as Java and JavaScript. Therefore, it's essential that we develop a way to systematically understand the kinds of vulnerabilities it can introduce. Towards that end, our work has focused on the automated induction and evaluation of JIT-based side channels. In our approach, we need to address two key questions. The first question is, how can we automatically determine if a side channel has arisen in a particular runtime state? And the second question is, since these side channels aren't present in every runtime state, how can we systematically explore different runtime states to find one that might be vulnerable? We address both of these questions in our work. I'll first show you how can we automatically determine if a side channel has arisen. If there are two partitions of the input space that are differentiable via their execution time behaviors, then there is a side channel in the runtime. To determine if this is true, we generate pairs of sets of evaluating input. In generating evaluating input, we ideally want to find partitions of the input space that are most likely to be separable. Returning to our motivating example, we gain the intuition that these are partitions of the input space that differ on some secret dependent branch condition. Our first step in automatically finding evaluating input is to perform dependency analysis to mark any branch condition in the program that is dependent on secret input. To the right, I show the program sanity safe, which takes two arguments, one of which, the integer a, is marked as secret. Then we generate an instrumented version of the program under test. For every branch condition, we introduce an integer variable that is set to 1 if that branch is taken, and set to 0 otherwise. For every loop, we introduce another auxiliary integer variable, which is incremented with each subsequent loop iteration. The end result is an instrumented version of the program under test, which for every input will generate a set of tuples that define the behavior of that program on branches and loops for that input. We use this instrumented version of the program under test in order to collect input tuple pairs. Finally, we partition the tuples into two sets of inputs based on a set of predefined patterns. At a high level, these patterns try and find partitions of the input space that disagree on some secret dependent branch, but agree as much as possible elsewhere. Now that we've generated these evaluating inputs, we can turn to our second key question, which is how we can systematically explore different runtime states. To do this, we use the fuzzer AFL to generate priming input. Priming input is program input that is used to prime the runtime to favor certain behaviors. We do this by repeatedly sending the priming input to the runtime. Even though AFL makes no guarantees in terms of coverage, empirically, we found it to be effective in generating priming input that exercises many different program behaviors. With our priming and evaluating input in hand, we can finally return to systematically fuzzing the runtime. We prime the runtime in favor of each priming input in turn. Then we use our evaluating input to automatically determine whether or not a side channel has arisen in the resulting runtime. We evaluated our automated approach on the Blazor, Themis, and difffuzz datasets, which have been widely used in the past for side channel detection. Each of these datasets consists of two types of programs: the original programs containing a side channel vulnerability and their fixed, supposedly safe counterparts. While we experimented on both, I show our results on the safe variants here. We were able to automatically introduce JIT-based side channels in the majority of these programs. In the Blazor dataset, we were able to automatically introduce JIT-based side channels in 13 of the 14 supposedly safe programs, a result which directly contradicts that of 4 state-of-the-art tools for side channel detection. In conclusion, we believe that our results demonstrate that any tool for side channel detection or quantification that doesn't consider the impact that just-in-time compilation has over these timing side channels is capable of missing this class of side channel vulnerabilities. Thank you, and I would be happy to take any questions or comments now.
Thank you, Tegan, for this excellent talk. So since there are no questions from the audience at this point, I have some questions. Sure. So your technique in order to detect JIT-induced side channel, you instrument the code. So I'm wondering whether this instrumentation itself influences the measurement of.
Yes, that's a great question. So in order to account for that, we only used our instrumented version of the program in order to generate the evaluating input. Once we were actually experimenting and trying to fuzz the runtime to determine if there were timing side channels, we returned to using the original version of the program. Because otherwise, yes, you're right, some of our instrumentation might get in the way of what the program actual timing behavior would be.
And another question that I have is, you're measuring side channels for the execution of the entire program, right? So is it possible to measure the side channels for code snippets, for instance, like your password example?
Right. So that would require, more refined timing capabilities. So sometimes it makes sense to assume the attacker doesn't have that, and perhaps in some other cases, an attacker or an observer might. Ultimately, there could be side channels present in smaller code snippets that get kind of obscured when they're included in the larger program. But I still think analyzing the smaller code snippets could be very useful. To gain, a better understanding of all the places where these vulnerabilities might occur.
Okay, thanks, Tegan, again.
Thank you.
And so, if you have questions to any of the authors, any of the presentations, you can visit the Baekje Slack channel again and post your questions on Slack. So there's going to be a quick break now, and after that, there's going to be the analysis and verification session. So then, thanks everyone for watching this XE episode on fuzzing. Bye.
Raul, go ahead.
Okay. Hello. Welcome to P28 Analysis and Verification. We have 4 talks in this session. And one of the 4 talks is an ACIP talk. And then we also have 2 demos today. I request audience to post their questions on the Slido window, which is on the left side of your Clouder. And I will take up these questions at the end of the talk. So first talk is by Renard from CMU. And he's going to talk about tailoring programs for static analysis via program transformation. So Renard, please start your talk.
Hi, everyone. Let's see if I can start up this video. It looks like I can't start my video, but let's go for the audio talk then. So, hi, I'm Renard. I am presenting tailoring. Now we can do it. Good. So hi, everyone. I'm Renard. I'm presenting tailoring programs for static analysis via program transformation. So there are many open source static analyzers out there today. I've put some examples on the slide, and they're useful. They find bugs, but we know that all static analyzers approximate. And one level that they approximate at is a theoretical level. So this is kind of the familiar issues of around decidability and soundness. But static analyzers also approximate at a practical level. In the interest of practicality, analyzer implementers may skip some language constructs. They may not model all of the functions in a program or library, and that can lead to false positives. For example, we might have an analyzer that forgets to model that a function like fclose closes a file, and now your analyzer might think that oh, you're not closing a file, whereas it's really just a limitation in the function model. So an interesting consequence of this approximation is that developers will change their code to work around some of these manifestations. And to make that concrete, this is an example taken from the rsyslog project, a common logging utility that's found on many Linux distributions. And what the developer did here was they changed this function and they annotated it with a comment that says, this is a Clang static analyzer workaround. And I can't go into great detail about what's going on here, but at a high level, what's going on is that this program change pulls out a constant string from a string compare function. And what that change does is it prevents a macro expansion of the string compare function. And that causes a follow-on effect where the analyzer no longer reports a false positive. So before this code was changed, it would report a false positive based on a very complex macro expansion. And so this kind of activity, this phenomenon prompts this question, why fix an analyzer issue in this way? It seems as if the developer went and changed their program because there was perhaps no option in the analyzer to turn that off or to suppress it. And we go into more depth in the paper. But the overarching reason is really that analyzers provide users with a set of configuration knobs, a set of settings that they can change, and these knobs are insufficient. The prevailing ways to specify, ways to tune your analysis is via command line flags, or you could maybe suppress various behaviors by annotating or suppressing how your code is analyzed with code comments. But these knobs are especially inefficient because the analysis authors implement these, right? They have complete kind of agency over how these knobs work, and if you as the user can't configure it for your project, then there's really no recourse. And so to go back to this example, one thing that a user can always do, a place where they have agency, is they can modify programs to change this analysis behavior. So it's really a powerful kind of knob that users always have in the sense that they can change programs to avoid things like false positives. So that's the motivation behind our approach, and we take this kind of manual ad hoc phenomenon and we present an approach that it generalizes it and automates it. So the first step in our approach is to present a way of syntax rewriting using declarative templates, very much in the flavor of the concrete example that I showed. So if we look at this code change, in our approach, you can specify a template to perform this transformation from that function that we saw before, and you can bind to certain elements in the program syntax and rewrite it and pull out that string constant. And so the main tooling behind our approach is a tool called Combi, which I wrote, and you can find more information about Combi online. But the general takeaway here is that it is a lightweight way of transforming program syntax that's more expressive than regular expressions, and you can kind of match and rewrite things that are particular to a programming language. So it works on many languages, it's lightweight, and it's fast. And so those are the key attributes that help our approach work. So besides this step of, and this mechanism of rewriting code, we also present our ideas as a way of temporary modification. So you might imagine that you have a CI running and you are changing your program with respect to an analysis that you're going to run. So it's a kind of pre-processing step. And we're not necessarily advocating, changing our program on a permanent basis to kind of make it work for the analyzer. It's a step that's especially tailored to known issues that you target for the analyzer that you're going to run. All right, so in our evaluation, we aim to show that this method of tailoring programs can improve static analysis, and we evaluate that along 5 analyzers. We do this also across 3 languages to give a sense that the approach generalizes. So we identified long-standing open issues on GitHub where users reported false positives, but there were no ways or mechanisms in the analyzers to handle those issues. And we go into more detail on those in our paper. So these were all developer and user reported issues, and we identified these issues by performing a commit search on GitHub. So to briefly go over our results, for those projects we analyzed, we wrote 9 of these templates, 9 of these rules to transform code, and we're able to remove 111 false positives across 15 of these projects. And again, we go into more detail about exactly the nature of those patterns and what they address in the paper. Just to give you a sense of how we evaluated things a little bit more deeply, we looked at especially large projects, so in the order of hundreds of thousands of lines of code. We wanted to show that this approach is feasible and efficient. So where an analysis might typically take in the order of minutes to run, we show that syntactic rewriting is fast in the order of a couple of seconds for these large projects. And then an interesting kind of thing to notice in our approach is that we can identify, for example, a false positive inducing pattern that we can remove for a particular analysis and project. And then we could reuse that pattern to identify other projects where we would also see that syntactic pattern induce a false positive and preempt it from happening if we ran that same analyzer. So overall, we demonstrate with these results that these local targeted transformations can improve analysis without adverse effects. So we can go in and actually tune these transformations at a general level in a way that they do not kind of cause other bad follow-on situations. So this is the summary slide of the talk. Thank you for listening, and I'll be happy to take questions.
Thanks, Renard, for a very nice, interesting talk. There are a couple of questions for you. The first question is, how do you guarantee that the changes you make or the programmer makes are semantically identical, even if syntactically different? So it's about the correctness.
Yeah, so that's a great question. First off, it's not necessarily the case that they are semantics preserving. In some cases, it may be a semantics altering change. And again, the thing to keep in mind here is that you're making a change, whether semantic altering or preserving, with respect to a known kind of analysis issue. So there is some assumption here that you understand the root cause of the issue, which is that perhaps the analysis doesn't give you a mechanism to change that. So there is some burden, let's say, on the person writing this transformation, to understand that doing that, taking that step and changing that program must be constrained to the extent that it's not going to introduce these adverse effects. Now, okay, how do we go about showing that in the paper? And it's basically, well, we assume the role of, I'm the analysis writer. Here is a conceivable pattern that you might write for this issue and taking into account, everything that the users reported, and then observing and running the analysis, making the transformation, running the analysis, and then observing what is the effect of that change on the analysis. Did it introduce additional reports? Did it cause other false positives or things like this? And we show in our results that, for all the patterns we evaluated, we didn't see these adverse effects. So it's a feasible kind of empirical observation that you can avoid them with, of course, the understanding that you're addressing.
I think we need to take, sorry to interrupt, because there are 2-3 questions there. In fact, I also had some questions, but I don't know whether we have time for it. So sorry, my apologies, but let me take the next question then. The question is, this work focuses on false positives. Would similar techniques work for performance issues in program analyzers? That is, some constructs are faster to analyze.
Yeah, I agree. I think it would be a wonderful thing to try and to look at constructs that we could trim away parts of the program that trip up analyzers, or strip out loops, for example, as a way of reducing the performance requirements.
Okay. Third question is, could you see the same approach to identify false negatives, for instance, by rewriting reflective call sites in Java?
I do. It's just not a dimension we evaluated on. Again, I think some of that will come down to looking at what issues exist where false negatives are missed, and it's a lot harder to find, when false negatives happen just by virtue of they don't appear. So I think absolutely the application is possible. It's a matter of kind of looking into those issues.
All right, Leonard. There are 4 questions, and please respond to these questions on the Slido itself, because right now we are running out of time. So let me thank you. Also thank the audience for asking wonderful questions, but let us move on to the next speaker now. So the next speaker is actually, it's a demo. It's a demo by Hiroaki from Fujitsu Labs, and he's going to give a demo of a tool for automated data-driven synthesis of repairs for static analysis violations.
Welcome to the demo of Phoenix, a tool for automated data-driven synthesis of repairs for static analysis violations. Phoenix learns from big code, such as GitHub, as to how people repair bugs. It fetches previous commits from big code, runs a static analyzer to obtain violations, and applies a violation tracking algorithm to collect repair examples. It leverages state-of-the-art programming by example techniques to learn generic, high-level repair strategies in a domain-specific language, which are used to generate suggestions to help developers repair bugs. In this demo, let's assume a developer is a part of the team developing the flight reservation system of an airline called Nimbus Airways. When you click the search button, the system gives you a list of flights that matches the given search criteria. Now suppose the developer implements a new feature in an IDE. Then a built-in static analyzer reports 2 new bugs. Unfortunately, developers tend to ignore such bugs, mainly due to lack of actionable suggestions from the tool. If the bugs are ignored, they will eventually cause serious problems. As you see, an internal error occurred due to the bugs, making the site completely unusable. Now let's use Phoenix to fix the first bug, a null pointer exception, likely crashing the application. To use Phoenix, you can simply click the bug you would like to fix, and select Run Phoenix. It brings up the Phoenix window where developers can browse the description of the violation and the repair suggestions. Finally, clicking Apply button applies the suggestion to the code. Now let's take a closer look at the Phoenix interface, using the second bug, which requires a more sophisticated fix. The first section shows an explanation for the violation, and the second section provides one or more repair suggestions. This time the Phoenix suggestion is a non-trivial, comprehensive fix that changes multiple lines of code. The last section further explains the suggestions by presenting examples of similar repairs mined from GitHub. In case developers are not confident about the suggestions, these examples serve as a hint as to how other projects have repaired similar violations. Once they become confident, pressing the Apply button will deploy the suggestion to the actual code. Finally, all the bugs have been repaired and there are no violations reported. Now the system is back to normal. By using Phoenix, the developer could repair a serious bug, thereby preventing loss of business. Thank you so much for your time.
This is it.
Thanks, Hiroki. Very interesting, demo. Let us move to the next talk, which is by Ganesh. Ganesh from Harmony, and the talk is on bespoke control flow analysis for CFA at scale. So Ganesh, you may start your talk.
Okay. Hello, everyone. My name is Ganesh Upadhyaya. I work at Harmony. It's a blockchain startup. I do program analysis, verification on smart contracts that are basically programs that run on blockchain. Today, I'm going to present our work on BCFA, which is a bespoke control flow analysis. It's a technique for performing control and data flow analysis at a very large scale, like millions of programs. This work was done during my graduate studies at Iowa State University under the supervision of my advisor, Dr. Hridesh Rajan. So the context of our work is data-driven software engineering, where the software-related data of a large collection of softwares is analyzed to understand and discover programming patterns, to infer specifications, for example, API preconditions, also to find bug suggestions, or even sometimes building models, machine learning models for bug prediction. There are plenty of applications that can utilize the data-driven methods in software engineering. The data-driven methods can be applied to analyze variety of software data. Source code is a prominent data that is analyzed. Different representations of source code can be analyzed. For example, source code text, abstract syntax trees, control flow graph, call graph, program dependent graph, etc. So in this work, specifically, we focus on data-driven software engineering tasks that perform analysis over control flow graph representation of the source code. A control flow graph is a source code representation in the form of a directed graph where nodes represent program statements and edges represent flow of control between the program statements. A control flow analysis traverses nodes to compute some information. It may visit some nodes several times and before finishing the overall computation on the control flow graph. A traversal strategy defines how to traverse this particular control flow graph. For example, there exist several strategies like reverse post order that traverses nodes before their successors, other strategies like post order, depth first, etc. So our problem is data-driven software engineering tasks that require performing analysis over millions of such control flow graphs. So, well, you may ask, what is the problem? So performance of these analysis heavily depend on traversal strategy selection. So we did some experiments for a particular data-driven software engineering task, that is inferring temporal specifications, and ran it over using different traversal strategies over a decoupled dataset that contained around 287,000 control flow graphs. As you can see, different traversal strategies took different amount of time. Using DFS strategy, the analysis took 70 seconds, whereas using RPO, it took 577 seconds. So you can easily see that using the right traversal strategy is important. Our second observation is that no single traversal strategy performs well across different analyses. In the bar chart shown here, we can see three sub-analyses of our software engineering task, that is inferring temporal specifications. We can see that WRPO strategy gives the best result for reaching definition analysis, whereas WPO gives the best result for dominator, and DFS gives the best result for collector analysis. So to summarize, the performance really depends on the traversal strategy that is selected, and no single strategy works best across different analyses and different graphs. So further, we will also see later in our experimental results is that choosing a bad strategy could even make the analysis infeasible. For example, it never finishes on larger data sets. So our intuition is that analysis properties and graph properties together influence the selection of traversal strategy. And our second intuition is also that we could automate the whole process of this selection of optimal traversal strategy for every individual analysis and graph. Note that it is important to automate here because otherwise it is infeasible to hand select while analyzing millions of such control flow graphs. So our approach is a bespoke control flow analysis. And the steps are as follows. First, we analyze all the sub-analyses or the traversals in the analysis itself to extract a set of properties about the analysis, such as data flow sensitivity, meaning whether the analysis is sensitive to the data flow between the program statements, or loop sensitivity, meaning whether the analysis is sensitive to the loops in the program, and traversal direction, meaning whether the analysis requires a certain traversing style. So next, we combine these analysis properties with the graph cyclicity, meaning whether the control flow graph has some conditional statements or loops. Together, we decide we decide optimal traversal strategy out of the given set of candidate traversal strategies. So this approach is repeated for every control flow graph in the dataset, meaning our approach picks an optimal strategy for every analysis and every CFG in the dataset. Let's dig a little bit deeper into how the decision is made, using the analysis property and the graph properties to derive an optimal traversal strategy. The figure here shows our decision tree that encodes analysis and graph properties. And the leaf node, you can see that these are the candidate traversal strategies. For example, consider the path leading to the leaf node P1. If the analysis is data flow sensitive and does not have any, the graph does not have any branch or loop, meaning it's a sequential program. In that case, our decision tree suggests using INC traversal strategy. So our paper contains details about why the decision tree is designed such way. So we evaluate our approach BCFA using a large collection of control and data flow analysis, such as shown in this table. The table here lists a number of sub-analysis denoted using TS, T1, T2, T3, and their properties in terms of data flow sensitivity, loop sensitivity, and traversal direction. For instance, the first copy propagation analysis has 3 sub-analyses, T1, T2, T3, and with the T2 being data flow and loop, data and loop sensitive, and it requires forward traversal direction. We ran the analysis on 2 large datasets. One is a DCAF dataset that contained around 287,000 control flow graphs, and GitHub dataset contained around 162 million control flow graphs. The table also shows some of the properties in terms of what percentage of them were sequential, branch, and loops. So this table highlights our key results. You can see in the first column, we list all the 21 analyses. And in the next column, split into DCAF and GitHub dataset. For each dataset, we show the percentage of reduction in the analysis time that our approach was able to obtain when compared to selecting just a single traversal strategy for all the graphs in the dataset. For example, for constant propagation analysis, our approach was able to reduce the analysis time by 17% when compared to simply using DFS strategy for all the graphs in the dataset. We have different color highlighting here to indicate the extent of the reduction in the analysis time. Greener is better, red and orange basically means that our approach didn't perform well. you can see that there are many dashes for the GitHub dataset, which indicates the analysis could not finish running even after several hours, basically supporting the fact that if you choose a wrong traversal strategy, it may make the analysis infeasible. So some of the takeaway points is that our approach is able to reduce the analysis time between somewhere around 1 to 28%, even if you choose and compare against the best strategy in each of the rows. And also note that there is no single strategy that is best across the rows here. So, and also the absolute numbers like corresponding to this 1 to 28% reduction can be several hours of saving. So the speed up of our approach obtained here is relevant both in terms of when you're using a paid infrastructure like AWS to perform your analysis, where you can save substantial dollar amount, or when you're using open and free public infrastructures like let's say BOVA, where due to the optimization of our approach, more concurrent users and analysis can be supported using the limited resources. So there are advantages. So several techniques have been proposed for optimizing the analysis implementation, specifically by proposing novel traversal strategies, mostly specialized for certain kinds of analysis. For example, Hind and Pioli proposed a new priority-based work list algorithm to traverse and process nodes for pointer analysis. The main difference is that our work does not propose any new traversal strategy. Instead, it selects the optimal traversal strategy on the analysis and graph properties, based on the analysis and graph properties. So to conclude, our paper proposes DCAF analysis technique for large-scale control and data flow analysis. It also proposes methods to automatically extract the analysis and graph properties required to make the selection of traversal strategy. And it provides a decision tree that optimally chooses the traversal strategy. And our approach is implemented in BOVA, which is a well-known open source infrastructure for mining source code, where we have seen 1 to 28% speed up, which translates to almost like 3 hours of time saving. So thank you for listening to my presentation. I'll be happy to take questions.
Thanks, Ganesh, for a very interesting talk. We have time for one question, but I think there is no question here. So let me ask you a question. Actually, two questions, I have. One question is, so I would like to understand it better. So I'm asking it for more kind of clarity. So do you analyze what kind of, analysis you want to perform, such as whether it's a bit vector analysis, not bit vector analysis, how many times it's going to iterate and all that, and then you choose that, right kind of a combination of, techniques for control flow analysis. And second thing is, second thing is, I would like to know whether you see kind of more generic applications of your work. For example, after all, it's about graphs, some properties, and efficiently, analyzing those graphs. So do you see any bigger or kind of wider applications, say biological graph systems or something? Have you thought about that?
Yes, to answer your first question, yes, we basically analyze the whole analysis or the task itself to derive some of the properties about the analysis or the task. Based on that, we make the selection. To answer your second question, yes, this technique can be generalized, but one point to note that it is only beneficial if you are trying to analyze millions of graphs or large number of graphs. So if you're analyzing only a small set of graphs or data set, it's not necessarily that you have to automatically choose the right traversal strategy. You can go with something like a work list based strategy that would perform somewhat moderate on different kinds of analysis. So when you're analyzing millions of such graphs, it makes really the difference.
All right, Ganesh, thanks for a wonderful talk. I think we need to move to the next speaker now. Next talk is on the recall of static call graph construction in practice, which will be given by James from Victoria University of Wellington. James prefers to give, play a pre-recorded video of his talk, but he will be available to take questions. So please post your questions in the Slido window. Okay, please play the recording. Sorry, I can't hear the audio. I do not know whether this is a problem with everyone.
It's a problem. Even
Yeah,
I can't
now
hear
I
it.
can. Yeah, okay.
Or Java bytecode to be more precise. And the problem is that if you have a Java program, like the very simple one in the box here, where a method invokes another method, then you try to model this as a directed graph, where the vertices are methods and the edges are invocations. And that has been around for a long time, so people have been researching this in great detail, and the problems or the challenges researchers have to deal with are precision, to deal with false positives due to devirtualization, for instance. Scalability, there are even some theoretical limitations to how scalable you can make this in terms of algorithmic complexity. And the problem we are concerned with, and we researched in this particular paper, is recall. So that's how to deal with false negatives, with things the analysis misses, and that has attracted more attention since publication of the Soundiness Manifesto in 2015. So the problem here is that in languages such as Java, you have dynamic language features like reflection. So in the code snippet we see here, we have a method we invoke. So the method is a reflective object that represents some method in the code. And now that method is typically instantiated with some strings. And now the static analysis has to reason about this and make a decision which method is actually being invoked. And that causes some obvious challenges. And reflection is not the only feature like this. You also have dynamic proxies, invoke dynamic class loading, unsafe, native calls, and so on. So there are quite a few of those dynamic language features which have been cataloged and studied before. So from a very abstract point of view, we try in a static or dynamic program analysis to capture possible program behavior. So possible program behavior is here as a Venn diagram modeled as the methods we can reach during execution. So that is really what call graph analysis is mainly concerned about. And then we can run a dynamic analysis that gives us known program behavior. And the easiest way to do this is, of course, to run test cases. And the static analysis usually over-approximates actual program behavior, but it also misses things due to the dynamic language features I said before. And so we are mainly interested in studying this space here where we know program behavior exists, so we can reach methods if you observe actual program executions. But the static analysis doesn't really capture this. And the one core metric we are concerned about is the ratio between this area of the dynamic of known program behavior covered by the static analysis and the entire known program behavior. And that is the ratio we call recall. So as a methodology, we have a dynamic and a static analysis. We basically diff and compare them. For the dynamic analysis, we run tests, and not only tests provided by the engineers, but also generated synthesized tests. And as a test generation tool, we use Avosud here. We aim for high coverage to get as many methods reachable into our model as possible. There are a lot of technical details here, which you can look up in the papers. There's a long discussion on this. So we have to unreflect the tests, we have to instrument the code, and so on. But basically, after we have done this, we record the full context call trees. On the static side, we use Dupe as a static analysis framework because it contains implementations of most mainstream call graph construction algorithms, and it also has support for modeling reflection. And we use different precision soundness settings and modelings of third-party libraries used by applications. So the data set used is a subset of the X corpus, so that is a set of executable programs that has been used in related studies. And we have 31 programs with generated and built-in tests. And when I make this claim, they are high coverage. Some coverage data, branch coverage data are below in this chart, and you can see different coverage charts for built-in, generated, and combined tests. What's really interesting here is that if you combine generated and built-in tests, coverage goes up, which shows some sort of orthogonality. And that in itself is probably an interesting finding. So research question 1 then was, how much does static analysis miss? And the answer is about 12%. So that's of course statistically across the data. So that is the median as seen in this chart. The static analysis used here is what we call the base analysis. So it's context insensitive and has no reflection support switched on. So then we move to a more precise analysis by switching on code graph sensitivity. And so the idea was that if you reduce the false positives, we might increase the false negatives as we are accidentally covered by the false positives, but we observe almost none of this across the data set. So there's a certain level of orthogonality between features that aim to improve precision and features that aim to improve soundness. Is reflection support effective? So we switched on reflection support, which was state of the art at the time. There has been development since we have done this, and that roughly halves the number of false negatives. So the answer is yes. However, it comes at a hefty price. So we set the timeout for the static analysis to 6 hours, and only for 20 of the 31 programs, the analysis finished within the timeout. So the statement here is across the reduced data set of 20 programs. Then, and that's probably the biggest chunk in the paper, we analyzed the sources of false negatives, and we did this with a couple of patterns and a technique we called CCT tagging combined with a dominator analysis. So I explain the simplest pattern here, and the simplest pattern is reflection. So the idea is we have our context call trees over here, and then from the static analysis we know what the false negatives are. So what's the static analysis? We compare this with misses. Then we tag methods such as method invoke, reflection, if we see it in the graph, and then we use a dominator analysis by just removing those branches, and we see how many of the static analysis false negatives are removed by doing this. And that really means that method invoke appears on the stack earlier, so that is a possible explanation that the static analysis cannot really make it past this point and reach M5 and flags it as a false negative. So there are more patterns like this. Some of them are more complicated when it comes to dynamic allocation, and we have a couple of tags defined for them, and roughly they fall into 4 categories. Dynamic invocations, that is method invoke, but also stuff like invocation handler invoke, dynamic proxies, and we have dynamic allocations. It's something like class new instance, dynamic access, field get, and a system category that covers methods without call sites and method called from system threads. So doing an analysis shows some interesting results because dynamic invocations or method invoke, for instance, only explains less than 10%, typically statistically again, of the false negatives, whereas dynamic allocation and system are the main culprits that can explain most false negatives. The other category is what we couldn't really categorize with this pattern analysis. For this, we did sampling analysis, and we basically found that it's the same patterns, but it's more kind of nested appearances of those patterns. An example for this are what we call double reflective factories that can explain most in this category. Yeah, coming to the conclusion, so the results can direct future research. You know, if you improve the soundness of your analysis, where can you focus on in order to have the maximum impact? Hybrid analysis is beneficial, of course, if you use something like Tamiflex. You have a dynamic pre-analysis, and then, of course, you can kind of combine the coverage of those two, and you have an immediate benefit. And we have some interesting characterization of generated tests, how they can contribute to improve coverage or improve recalls. However, there are certain limitations, and they are not as good as built-in tests. And again, I have to refer to the paper for details. So that brings me to the conclusion. Thank you for your attention. I would like to acknowledge the project sponsors, which is the National Science Challenge of New Zealand and Oracle Labs. Thank you again for your attention.
Thanks, James. Very interesting talk. Let me see if there are questions. I have a question though. My question is, a very interesting work, and I see that, from Java perspective. So how do you expect your observations to change across languages? So this is for Java, but what do you expect for other languages?
Well, that has to be studied. You know, whatever I could say now would be highly speculative. I've spent some time early in my career in industry, and we worked with Smalltalk. I would kind of expect that in Smalltalk that ratio would even be higher. Or Smalltalk is, of course, now pretty much an outdated language, but this kind of legacy lives on in languages like Ruby, and I would expect that the problem is even worse there.
I see.
In terms of recall, so you would get if you did a similar study, you would, I think, likely get a lower recall. Yeah.
So I think in your paper you say that reflection is not the only or not even the main cause, right? If I remember correctly.
Yes.
So considering that, what do you think, about, for example, the other languages, which are in popular use, like, say Python, C++, JavaScript, and, do you think that, this analysis is even more important there, less important? Any ideas for future work? Do you think that that kind of study makes sense, is important?
Well, I think the purpose of the study was to direct builders of static analysis to where to best invest effort in order to model those features, because it's really, really expensive to do so. And it's first of course expensive to design the analysis, but then also for the user expensive to run it, because there's a lot of computational overhead. And part of this is reflected in our study when we started to switch on those features in Drupal. And it turns out that as often, a lot can be done by just picking low-hanging fruits first. For instance, by modeling system threads, or by modeling things like we have a Java virtual machine calls method, so that the methods don't have a call size. And of course, many static analysis will just miss this. Yeah, but yeah, so we hope to give some guidance and focus to static analysis builders what to do.
Okay, yeah, it's very important. Okay, thanks a lot for nice talk.
Thank you.
Let's move to the next speaker now. The next talk is ACIP talk. It will be given by Chetan from MSR. And the talk is on diagnosing and triaging performance issues in large-scale cloud services. So Chetan, you may start with.
Thanks. Hey everyone, this is Chetan Bansal from Micro Research. I'm a research engineer working on AI ops and other related areas at Microsoft. Today, I'll be talking about some recent work on diagnosing and triaging performance issues using machine learning in large-scale cloud services. This is joint work with my colleagues at Microsoft. So yeah, so before we go into the details about what the framework we have built, I wanted to talk briefly about the motivation behind the work. So at Microsoft and any other large-scale cloud company, we are operating about like hundreds of services, and usually most of these services have KPIs or key performance indicator, which are tied to customer revenue and satisfaction via service level agreements and service level objectives. And some of the common metrics, which are performance indicators, which are monitored, are latency at different percentiles, availability, failure rate, etc. And one common challenge we have seen across multiple teams at Microsoft is that root causing regressions in these KPIs is very laborious and requires very deep domain knowledge about the environment and the services. So some of the key challenges we have seen while working with different product partners at Microsoft are, first, a lot of these services generate huge amount of telemetry of the order of even terabytes per day. And often these logs and telemetry contain mixed attributes, such as they be continuous and categorical attributes. For example, you can have performance counters, which are continuous. You can have subcomponent latencies, and you can also have categorical attributes like your build version, your operating system, your environment, region, etc. And some of the prior work in this, most of the prior work in this area is focused on the logs with continuous attributes based on anomaly detection or trend analysis. And the last challenge we noticed was high cardinality and dimensionality of the logs attributes, which makes any brute force approach non-feasible and non-applicable to this challenge or this problem. I also want to briefly talk about some practical constraints or practical experience in terms of performance regressions. So often, a lot of these engineering teams which are operating these services have limited resources. So they can only focus or investigate issues or regressions which are causing major regressions, basically which move the needle at a macro level on your KPI. Second, because of the high cardinality, you can have like millions of slices of data, and oftentimes the regression might have a narrow impact on a few slices or a few subscribers, few tenants, and it's not possible to do things like anomaly detection or manual detection at that high cardinality. The third challenge we have seen is that a lot of times, again, the regressions are impacting a very non-linear slice of data. For example, only a certain set of users on a particular operating system running a particular build might be impacted. So oftentimes those regressions go unnoticed. And the last thing is that we want to do proactive detection so that we can find, detect, and mitigate issues before they're reported by the customers or escalated by the customers, before they impact customers, basically. So here I want to briefly talk about the DCAF framework, which we have built and deployed at Microsoft. So at the first step, what we do is we basically collect the logs and telemetry at a regular cadence, like daily or hourly, based on the scenario requirements, and then aggregate them in a common big data cluster. From there on, we basically run the DCAF framework, which first has a step for feature selection. And that's a semi-automated step for which involves domain knowledge, so that the service owner can basically select or give input about which attributes have been useful in the past. And the second reason is to basically prune attributes like correlation IDs or IP addresses, which are not going to be useful for finding macro level or at a higher level issues. Here, we are not really interested in finding issues which impact a single user. So we get rid of those attributes automatically based on cardinality. That helps save compute and also like runtime efficiency. Then we do an optional data sampling step in case, like, because if you're talking about terabytes of telemetry per day, then you have to sample to be able to leverage machine learning and other like data science techniques for that. Then once we have the data set, we basically leverage a random forest ML model. And one key thing I want to highlight here is that unlike traditional machine learning, we don't use the models for prediction, but we train the models and analyze the model to extract patterns which are correlated with regressions. I'll briefly talk about that in the next slide. Finally, once you have the model, we extract these patterns, rank them, deduplicate them, save them in a database, and then send out alerts and reports to the service engineers or the service teams or the engineering teams, who then act on them and trash them and leverage these alerts to mitigate the issues. So let's briefly talk about how we localize the performance issues based on the random forest model. So as I said before, we basically train the model. So random forest models are supervised models, right? So you need to have a label. So here our label is basically the KPI, which can be, for example, latency, availability, failure, which you want to diagnose. Once we have trained the model, we basically parse the decision trees or the classification trees, regression trees, and extract the patterns which are correlated with the regressions. Here on the bottom right, you can see an example of an issue which was localized using DCAF. So here it basically highlights a very specific population, which is basically like any request which was handled by this server farm with auth latency more than 40 milliseconds in the European region. And it also highlights other metrics such as what was the impact on the latency and how many requests or users were impacted. So using these metrics, the on-call engineer or the on-call engineer can basically rank or triage these issues more effectively, or prioritize these issues more effectively. Another thing I want to talk about is why random forest model compared to other ML models. So a couple of reasons. One, they're highly interpretable. Second, they work on heterogeneous attributes and also labels, because we have both regression trees and classification trees. And third, since a random forest model is basically a multitude of decision trees, we can parallelize them and scale them more effectively compared to other models. Then I also want to briefly talk about triaging step, because that's something we added based on feedback from product teams. basically a DCAF generates reports with tens of results, right? But for the on-call engineer, given the time constraints and also they're like operating real-time services, so they need some sort of classification to be able to effectively use the results. So basically, we've categorized all the results into different categories based on historical results from DCAF. So basically, we given a pattern, we classify into a new, regress, or top impactful category. So then the on-call engineer can have a better idea about how to consume the results, and they can focus, for example, only on the new issues or on the most impactful issues, etc. And this is done based on, as I said before, a moving 14-day history of the results, and by using the standard deviation of the metrics, which I just talked about. To summarize, we have basically built DCAF, which is an ML-based framework for localization and triaging of performance issues. And even though we started with performance, we are also using it for things like crashes, and also even economic metrics like the user monthly active users, etc. DCAF has been successfully used to detect and triage several issues across multiple services, and now we are expanding beyond services to even client applications, where we can understand issues which the users of the clients like Microsoft Outlook, etc. are facing. And lastly, based on the case study we did, we saw that DCAF helps significantly reduce the manual effort in the investigation of the regressions. And in terms of future work, so DCAF is currently focused just on the telemetry and the logs generated by the services. In future, we want to use DCAF. We want to extend DCAF to work on unstructured logs, which is a limitation today, and also tie connect the logs to the actual code changes which go into the deployment, so that we can do an end-to-end diagnosis of code and performance issues. Thank you.
Thanks, Chetan, for a very insightful talk. I don't see any. Oh, there is a question. Let me take that question first, and then I have one question. So have you considered more traditional queuing model-based approaches to solve the problem?
I missed also more traditional what?
Have you considered more traditional queuing model? Queues.
So I'm not familiar with those techniques, but if there anything, if you can share any pointers, I'm happy to look into it and get back to you.
So maybe I will request whoever asked this question to maybe clarify that thing. But let me, in the meanwhile, maybe I will ask a question. So do you think that your triaging method, the new automated approach based on DCAF, what is the worst case of that? So overall, you achieved a lot of time, and it's effective. But do you think that sometimes it can go drastically wrong because of some long kind of predictions and long triaging, and the cost of that is also significant?
Right. So that's a good question. So I think that I have 2 points which will help answer the question. First, is DCAF currently is more of a recommendation system. Like it basically recommends what cohort of population might have a regression. So that's basically something for the on-call engineers to look at. But even if DCAF even if that doesn't make sense, then the on-call engineer would anyway do the investigation which they would have done otherwise. So it's basically like a low-cost way to proactive way to highlight regressions. But if it is not able to detect, then the on-call engineer would still have to do what they did before. And then the other point was that, so one of the limitations we have seen is that DCAF focuses on correlations and not causation. So oftentimes it will help you localize the issue, but it may not pinpoint to the exact issue. For example, there was a specific regression where there was a particular server rack which was affected, which was causing high latency. But because the logs didn't contain component level information, it just highlighted the rack. So it just pointed out the correlation, which was still useful, but the on-call engineer still had to dig the logs deeper and figure out what component, the auth component, was actually timing out.
All right. Okay, thanks, Chetan. We have a time constraint, unfortunately, so I will not be able to ask another question, but we can take this offline. I will also request whoever asked the question to ask the same question with some clarification about the queuing model to Chetan.
Thanks,
Is that okay? Okay, thank you very much. So with this, we will move to the last demo of this session. This demo is, So this demo will be given by Kush from UT Austin, and tool is on mutation analysis for CoC verification projects. So I request to play this demo.
I don't think I can hear it.
Yeah, I cannot. So I wasn't sure whether it is sound or so. I expected sound, but I can't hear.
For this demo, I will run MCock demonstration for MCock, a mutation proving tool for CoC with capability for fast parallel proof checking. I'm Kush, and I'm an undergraduate student at UT. This is joint work with Carl from KTH, Ahmed from Facebook, Amelia from INRIA, and Milos from UT. I will now show you how to run MCock. At this point, the user has already cloned your MCock repository and followed the setup instructions in the README. For this demo, I will run MCock on a publicly available project, StructAct. The same sequence of steps I show can be used to run MCock on any project. To run MCock, simply run the MCock Python script. You'll need to provide the following information. This includes the project or the name of the project that you are running, the SHA or the Git commit ID, the URL or the GitHub repository URL, the build command, which is the command used by CoC to build the project, and either the qdir or rdir attributes used by CoC in compilation. Now we will run StructAct. Right now, MCock is applying our operator to each segment of the code within this project and generating one mutant at a time. For each mutant, we perform proof checking. We optimize this process through incremental analysis and parallel execution. Now we will view the HTML report generated by MCock. You will now see our table view, which consists of all the files in a given project and their number of generated and killed mutants, along with their mutation scores. We use green for files with a mutation score of 100%, red for files with a mutation score of 0%, and yellow for all other files. To see the statistics for each operator in a file, we can click on Expand. Additionally, we can find information at the top of the report, such as the total running time, the mode of MCock we were running, along with the total number of equivalent mutants. To see more information about a given file, we can click on its name. This brings up our code view, where we can see all the mutants at a line-by-line level. We use green for lines where all mutants were killed and red for others. To see what operators applied on that line and their number of generated and killed mutants, we can click on View Operators. Thank you very much for watching this demo. For more information,
Thanks, Kush, for a very interesting demo. With this, we have reached the end of this session. Let me thank the speakers. Let me also thank the participants, audience, and very importantly, the online event management team. We've done a wonderful job. So thanks, and see you in the next session.